neural networks, the technology behind ChatGPT, image recognition, voice assistance, and basically every AI breakthrough you've heard of. Everyone talks about them, but most people have no idea how they actually work. Today, we're demystifying neural networks without drowning in math. By the end, you'll actually understand what's happening inside these systems. Neural networks are inspired by the human brain. Your brain has about 86 billion neurons, each connected to thousands of others. When you think, signals flow through these connections. Some connections are strong, some are weak. Artificial neural networks work similarly. They have nodes like neurons connected by weights, like the strength of brain connections. But here's the key difference: we are not simulating a brain, we're borrowing the basic idea and implementing it with math. Think of it like how airplanes are inspired by birds but don't flap their wings. Neural networks capture the essence, interconnected nodes passing signals without copying biology. A neural network has three types of layers: input layer, hidden layers, and output layer. The input layer receives your data. For image recognition, each pixel might be one input. For text, each word token is an input. Hidden layers are where the magic happens. They process the inputs through weighted connections and transformations. You can have one hidden layer or hundreds. More layers means the network can learn more complex patterns. The output layer gives you the result. For a cat detector, it might output a probability, 80% likely to be a cat. For text generation, it outputs the probability of each possible next word. Data flows forward through these layers, getting transformed at each step. This is called a forward pass. The network takes your input, processes it layer by layer, and produces an output. Two key concepts make this work: weights and activation functions. Weights are numbers that control how much each connection matters. A high weight means that input strongly influences the output. A low weight means it barely matters. When we train a neural network, we're essentially finding the right weights. Activation functions add non-linearity. Without them, no matter how many layers you stack, you just get a fancy linear equation. Activation functions let the network learn complex curved patterns. The most common one, ReLU, is simple. If the input is positive, pass it through. If negative, output 0. This tiny bit of nonlinearity is surprisingly powerful. Together, weights determine importance and activations add complexity. Stack enough of these transformations and you can learn almost any pattern. Now the crucial part: how does a neural network learn? It starts with random weights. The network makes predictions and they're terrible because the weights are random. Then we calculate how wrong it was. This is the loss function. The bigger the loss, the worse the prediction. Next comes backpropagation. We trace back through the network asking which weights contributed most to this error. This tells us how to adjust each weight to reduce the error. We nudge the weight slightly in the direction that reduces error. This is gradient descent, following the slope downhill toward better predictions. Then we repeat. Show another example. Calculate error, adjust weights. Do this millions of times across thousands of examples. Gradually, the weights converge to values that make good predictions. This is training. We're not programming rules. We're letting the network discover its own rules by adjusting weights to minimize prediction errors. Here's something fascinating. In deep networks, different layers learn different things. For image recognition, early layers learn to detect simple features: edges, colors, basic shapes. Middle layers combine these into more complex patterns: textures, parts of objects. Later layers recognize high-level concepts: faces, cars, animals. Nobody programmed this hierarchy. The network discovered it automatically through training. It figured out that detecting edges first makes it easier to detect shapes, which makes it easier to detect objects. This automatic feature hierarchy is what makes deep learning so powerful. The network builds its own ladder of increasingly not all neural networks are the same. Different architectures work better for different problems. Feed-forward networks are the basic type. Data flows in one direction, good for classification and regression. Convolutional networks, or CNNs, are designed for images. They use filters that slide across the image, detecting features regardless of position. This is why they're so good at recognizing objects anywhere in a photo. Recurrent networks, or RNNs, have loops that let information persist. They're designed for sequences like text or time series. Transformers are the latest breakthrough. They use attention mechanisms to weigh which parts of the input matter most. GPT, Claude, BERT, all transformers, they've become the dominant architecture for language. Here's the practical intuition. A neural network is a function approximator. You show it inputs and desired outputs, and it learns a function that maps between them. It doesn't understand anything the way humans do. It finds statistical patterns in data. When ChatGPT writes convincingly, it's not thinking, it's outputting the statistically most likely next tokens based on patterns learned from trillions of words. Understanding this removes the mystery. Neural networks are powerful but not magical. They're sophisticated pattern matchers that we figured out how to train effectively. What you learned: neural networks have layers of nodes connected by weights. Activation functions add nonlinearity. Training adjusts weights to minimize prediction errors through backpropagation. Different architectures suit different problems. Next video will cover how models actually train, the optimization process in detail. Subscribe for more actually useful AI explanations. See you in the next one.